Today I'm going to share with you the mind mapping for the topic of electrostatic and electricity. Okay, let's start with a discussion of electric charges. So we know that there are two types of charges. One we call it as positive charge, another one you call it as negative charge. Example, positive charge has a magnitude of positive Q1, negative charge has a magnitude of negative Q2. If they are separated by the distance of R, okay, so you know that one is positive, one is negative, so there will be an attraction force exists between them with the magnitude of F and F. Okay, so according to a law, the magnitude of the force can be obtained from a law called it as Coulomb's law. According to this law, the magnitude of force is directly proportional to the magnitude of the product of these two charges, inversely proportional to the square distance between these two charges, and the proportional constant is K, where K we call it as Coulomb constant. Okay, K is called it as Coulomb constant. Okay, this is the magnitude of force exists between these two charges. So we also know that surrounding the force, there is the electric field exists surrounding the charges. So electric field exists surrounding the charges. For a positive charge, electric field is directed outward, and for the negative charge, electric field is directed inward. Okay, so this one is the line I draw here is called it as electric field line. So according to the definition, electric field E is defined as force per unit charge. So according to Coulomb's law, force is K Q over R square, and electric field is defined as force per unit charge, so per unit charge. Therefore, electric field of E is equal to K Q over R square, where the unit of our electric field is Newton per Coulomb. Okay, so this is electric field. So this is the parameter for electric field. The other one is electric force. Then after that, we learn on the relation between the work and energy. So in mechanics, we learn that work done is equal to the negative change of potential energy. So change of potential energy means we are using final potential energy minus the initial potential energy, right? So we have another term, call it as electric potential. So what is electric potential? Electric potential is V. It is defined as potential energy per unit charge, right? So this is electric potential energy per unit charge. Therefore, the difference, the electric potential difference, so this one we call it as potential difference. Sometimes it can be also called it as voltage, right? Voltage, it can be same as a potential difference. So potential difference, therefore, is equal to the change of potential energy to the unit charge, right? So we know that the change of potential energy is equal to negative work done, because work done is equal to the negative change of potential energy. Therefore, the change of potential energy is negative work done per unit charge. Okay, so that is how you define the potential, electric potential, and potential difference. Okay, other than this, we can also state the potential difference in terms of force. Okay, we know that potential difference is work per unit charge. So work is defined as force multiplied with displacement. So per unit charge, it is negative, so add a negative there. So happen force per unit charge. Force per unit charge is actually electric field, right? It's actually electric field where we have defined over here. Force per unit charge is electric field. And from here, there is a relation where we can relate the electric potential with electric potential difference with the electric field, right? So this electric field here can be also related to electric potential can be also related to the potential difference of V. Okay, potential difference of V, where delta V is the potential difference. Delta V is the potential difference. All right, I just rearrange only. Move the delta D to the other side of the equation. Okay, so this is another subtopic. And now, if I rewrite this electric field and the electric potential difference in terms of integration, it can be written as delta V is equal to negative E delta D. So instead of delta D, I can also write it as, use another term, call it as R, which is a distance, right? So delta V equal to negative E delta R, or I can write it as dV equal to negative E dr. So I integrate both sides of the equation, and I will get V is equal to E negative E dot dr, right? E is actually, just now we have derived it out, E is actually equal to kq over r squared. So we substitute in negative kq over r squared dot with dr, right? So where integration of 1 over r squared, dr is equal to negative 1 over r plus c. So I will get negative is positive, kq over r plus c. So we define that the electric potential at infinity is equal to 0, therefore c is equal to 0. So this is the expression for the electric potential due to a point charge, right? So electric potential due to a point charge. So when you use this expression, we must consider the sign convention of Q. Must consider the sign of Q, right? So now let's move on to equipotential surface. So equipotential surface means a surface which has the same potential. Equi means same. Equipotential surface, right? Is a surface with the same potential. So this potential here is referred to electric potential, and therefore the work done for the equipotential surface is equal to 0 because they don't have a potential difference, right? So what is it? So we can refer back to here. Potential difference is equal to the negative work done per unit charge. So equipotential surface, that means they have the surface has the same potential, therefore there's no potential difference, and the work done along the equipotential surface is equal to 0. Okay, so now let's move on to another part, another law, call it as Gauss law, which is important in this electrostatic. So Gauss law. So according to Gauss law, the total charge enclosed in a Gaussian surface is equal to the integration of d dot dA. So this d is capital letter D is a vector quantity. We call this as electric flux density, okay, which has the unit of Coulomb per meter squared, where D is closely related to the electric field. We have just learned what is electric field, where D is equal to epsilon naught E, right? Epsilon naught E. And therefore, the total charge enclosed, according to the Gauss law, is equal to epsilon naught E dot with dA, right? So when you integrate dA, A stands for the area, surface area. So when you integrate the A, you will get A, okay? And therefore, integration of epsilon naught E dot with A, integrate of dA is equal to epsilon naught E A cos theta, where theta is the angle between E and normal of A. Okay, so this is Gauss law. So why there's a cos theta here? Because E is a vector quantity and A is also a vector quantity. So basically, we are using the dot product between two vectors. So dot product between two vectors means, if you can remember, we learned that A dot B is equal to, dot product between two vectors is equal to magnitude of A, magnitude of B, cos theta, right? That's how you get the cos theta there. So this is Gauss law, right? So this is Gauss law, Gauss law. And if we combine what we have learned, the Gauss law, with the definition of the electric potential, we can apply this concept to the capacitor, right? We applied these two concepts and applied it in capacitor. So capacitor, basically, we learn on the parallel plate capacitor. For example, we consider two parallel plate capacitor. This is a parallel plate capacitor. It's connected to a potential difference or the EMF of E of V, right? So let's say on the left plate it will be charged to a positive charge, on the right plate it will be charged to the negative charge. And in between these two plates, electric field exists between the plate because there is existence of a positive charge and negative charge on the plate, right? So we define that the capacitance is defined as the ratio of the charge. Charge here is a charge stored on each of the plate, positive Q and negative Q, right? So capacitance is defined as a ratio of the Q to the V, where V is the potential difference between the two plates, okay? So according to Gauss law, right? According to Gauss law, the total charge enclosed total charge enclosed is equal to epsilon naught EA cos theta. So if you apply this Gauss law on the capacitor, the angle between the E and normal of A is basically 0, right? The angle between the E and A of the capacitor is basically, the area of the plate is actually equal to 0 because E is parallel to the normal of the plate. This is the normal of the plate, right? And therefore, I will get the Q as epsilon naught EA because cos 0 is equal to 1. So divided by V, right? Divided by V. So what is V? So V stands for potential difference or the electric potential, where V is equal to E multiplied with G. V is equal to E multiplied with G. So V is equal to E multiplied with D. So eventually I will get the capacitance of a capacitor as epsilon naught A divided by G. If epsilon naught here, we call it as the permittivity of free space. Permittivity of free space. Okay, so if you place the parallel plate capacitor, you insert the insulator in a parallel plate capacitor, so generally the capacitance of the capacitor is epsilon naught epsilon R A divided by G. Okay, so for your information, epsilon R for air and epsilon R for vacuum is approximately equal to 1. So that's why for air and vacuum, we usually don't write the epsilon R terms here, right? So this is capacitance. We applied the Gauss law and the definition of electric potentials to derive out the capacitance expression. Okay, so this is a capacitance. We know that the electric potential V is defined as potential energy per unit charge. That is V equal to PE over Q. So if we rewrite the expression, it could be written as PE equal to QV, where V is the electric potential due to a point charge. So we have derived out that the electric potential due to a point charge is equal to KQ over R. So we substitute into the expression. V is equal to KQ over R. Therefore, the potential energy is equal to KQ over R. Okay, so when we use this expression, we must consider also the sign of the charges. Must consider the sign of the charges. Potential energy is defined as a product of QV, right? That is potential energy. So now I'm going to show you what is the energy, total energy stored in a capacitor. So energy, potential energy or energy is Q, the product of Q multiplied with V. So in a capacitor, so the total energy stored is the integration of V dQ, right? Where V is a constant. And from the definition of the capacitance is equal to the ratio of Q over V. Therefore, V is equal to the ratio of Q over C. So I substitute in Q over C dQ. So the capacitor will charge from 0 charge to the maximum charge of Q, and integrate the Q with respect to dQ, we will get Q squared over 2C. Okay, this is the energy stored in a capacitor. Or you can write, if you are using this relation, C equal to QE, we can also express the energy stored in a capacitor instead of Q squared over RC in another term, okay, where Q is equal to CV, so Q is equal to Q square is equal to C square V square divided by C. So U can be also expressed as half C square. Okay, so this is another way for we to express the energy stored in a capacitor.